Hello guys. Well, we're back. We're going to start talking about, we're going to answer the question that you guys answered, that I gave you and some of you've answered. One thing I got to say, you guys are really good. I'll give you that. I got some really brilliant viewers. I left some stuff open on that, and one of the reasons why is I just wanted you to think a little bit. I could have set the questions up that everything in the circuit was perfect. You know, perfect conductors. They don't have no resistance. Perfect battery that has no internal resistance or anything. Will supply voltage forever. Perfect light bulbs that the resistance, what resistance is in them, stays the same no matter what. Perfect capacitor that there's no resistance in it, there's no leakage in it, no nothing. But that's not exactly the real world, and I wanted you to think about it a little bit. And you guys did. You guys did wonderful. Alright, on the first question, does current flow through a capacitor? Well, in order to answer that, we must look at current and try to decide what it is. Back in the day, and even today sometimes in a lot of technical schools and colleges, it was thought that current flowed because of electrons. That the electrons moved through the wire and kind of think of it as like a pipe that's filled full of marbles, and right now there's no voltage hooked to it, and I hook a battery to it, then it would be like some marbles start coming out of the battery, and I start shoving at one end of the pipe, and at the other end a marble comes out. Each time I shove one in, one comes out, and continues doing that. Well, that's the way it was thought, and that's called electron flow. If you take engineering or you take physics or something of that nature, you will learn real quickly that a different type of current flow, and it's called conventional current. When in conventional current, we don't look at electrons, we look at charge. And basically what that means is electrons you can think of as pockets or packets of negative charge. And each electron you can think of having a negative charge of 1. It doesn't matter what 1 means or what dimensions it has, it's just 1. Alright? And, you know, atoms are made up of electrons and protons. When they're equal, when they're neutral, they have the same number of electrons as do protons. Each proton has a positive charge of 1. Okay? So, when you're looking at actual charges that happen in electricity, like in, say on the capacitor or in a wire or what the battery's trying to produce or anything, then in that case positive charge would be like a lack of electrons. It can be just a single electron, it can be several electrons depending on the atom, depending on what it is. And a negative charge is like an abundance of electrons, too many electrons. So now that that's explained, exactly how is current flow in that theory? See, in the electron theory, current flowed from negative to positive. In charge or conventional current, current flows from positive to negative. And what they call the positive charge is holes. It's just a representation of a single atom that is there that's missing an electron. So it's kind of like there's a hole there. And they feel that, you know, in physics and in electronic engineering and electrical engineering, that the charge that's moving is the positive charge. The electrons don't actually move. They just kind of vibrate back and forth. They'll jump from one atom, then back to another atom, in, say, the wire, or the battery, or whatever. So when you look at it from that standpoint and think about charge, and we'll go into this a little more in our video, but then what's actually happening on the capacitor is, as I won't draw the rest of the circuit, but as the battery is supplying juice to the capacitor, one side is starting to get abundance of positive charge, and the other side is getting abundance of negative charge. Now, the instant that the battery is turned on, okay, we do have a current flow, and what happens is, as more positive charge is coming out of the battery and trying to build up here, we get a negative here that starts building up because the two are attracting each other. But we do have a wire, a conductor that's coming back to the battery that will start bleeding off some of this. As this comes in and builds up, it starts bleeding off some of this. Now there will be some jump overs, just influence of charge there, but that's leakage, so it's not really a large amount. Now there is one little problem with this. As the circuit runs with the battery, it can only move it so long. It continues to build up and build up and build up because it's coming out. The energy is, the charge is coming out of the battery so fast the capacitor can't keep up and can't keep bleeding off this. So it'll continue to build up and build up and build up. But in the early time, it's the influence of that charge that allows the flow. So in theory, it is flowing through the capacitor. So the first answer is yes, it does flow through the capacitor. What's flowing through the capacitor is the charge, or more, the influence of charge is flowing through. Because we influence things by the charges coming to it and the charge leaving, and we give it a pathway to leave. Now, the second question: does a capacitor ever fully charge? And the answer to that is actually no, in a nutshell. But in the practical world, being we don't have a means of truly measuring minute currents, extremely small currents, then in a practical world, yes, it does charge up. But in reality, and really what really happens, it doesn't. And the reason is, if I draw a graph of it, which again, I'm not only drawing around this thing, excuse me, around the tripod, but I'm not real good at drawing. Anyway, if we say just call this I, current flow, and this is time. Initially, we got 0 here. So initially, we start out right here. We turn the switch on. Current starts flowing very quickly, but very quickly it starts dropping. Then it does this number. It starts bending and bending, and it just keeps going and going and going and going. Getting ever so closer and closer and closer to 0 current. But it never ever comes in contact with that line. Now, in a practical sense, being that we can only measure down so small with even modern day equipment, there's a point that we'll see it still flowing, and then in the next instant it just drops off to 0, because we drop below. The current flow actually will then drop below the threshold that meter or whatever device we're using can read. So it will actually appear like that. but the actual curve actually looks similar to this. My drawing's terrible. This is called an exponential curve. An exponential curves, one of the big things about them is they never go to zero. They never cross that line. They never come in contact that line. They have this unique little bend in them. And, you know, yes, in a practical world and real world, there's some resistances and some things like that and stuff that's going on in that circuit, you know, due to resistance in the capacitor, and there's some leakage in the capacitor, and there's resistance in the wire, and so on. All that does is kind of shift this a little bit, but that's all it does. You know, it just extends the time just a little bit, so it shifts this just a tad bit. That's all it does. Otherwise, it's the same curve. Now, why doesn't it? Why doesn't it go to zero? Well, in math, and I know I'm getting in math, there's a number sequence that we can look at that represents this. If our time, if we look at the current versus time there on that curve, if we look and plot out what's going on there, we'll find a number sequence that looks something like this. And actually, we're going to make this negative so that the rest of it can be positive. So we go 1/2, and then if we go half again, we go 1/4. We go half again, we go 1/8. We go half again, we go 1/16, 1/32, 1/64, and dot dot dot. Forever, ever, and ever. Okay, the reason I put -1 in here is because it's actually, if I look at the current, I'm reducing current. Otherwise it'll be 1 minus 1/2 minus 1/4, which works, and it works fine, but it's neater this way, so we start off with just minus and 1. Now, we don't have to worry about the 1 because that's, you can kind of think that as the starting point. So what's happening with the rest of this? Well, this approaches a number, but it never gets there. Now, if it was all minuses, I could say it approaches 0, and if it's all pluses, I can say it approaches 1, and 1 minus 1 is 0. So, in a real sense, I can actually say that this part here will eventually equal 1. But it approaches 1 as I keep going. But I have to set a limit, and I'll go into that later in some other examples. But the basic idea is, if I could take this out to infinity and add it all together, it would come up real close to 1. And what the limit is what happens with this bottom number. As this bottom number goes to infinity, and this goes to 1. The whole point of it goes to 1. But as you can see, these just keep doubling, so this fraction stays here. This thing doesn't absolutely, positively ever really completely add up to 1. It just goes on and on and on. But it is what they call a convergent cycle, meaning that it's converging onto something, in this case 1, but it never gets there. But that's why, in a nutshell, it's not ever really fully charges, because it never actually fully takes away the current, ever gets to 0. I hope that kind of helps you. You guys had excellent answers. Most of you actually got the answers right. And you thought through the thing. The main thing I wanted you to do is think. I wanted you to think about a problem. And the reason for that is because sometimes, well, a lot of times, when you're working on a radio and you're troubleshooting it, and you might be able to get it down to a circuit using test equipment and find, hey, it's this circuit that is my problem area. But then at that point, you start having to think. Because if you don't, then you end up just part replacing. You just start replacing all the parts in there until maybe it finally works. But in actual troubleshooting, you actually have to think and work through the problem in your mind of what's going on there and what could be going wrong. So that's why I wanted to do this. Now, I'm hoping I can get through this. This thing's run longer than I anticipated. We're going to at least get an introduction to capacitance. We'll talk a little later in another video about how they react in an AC circuit, parallel capacitors and series capacitors and stuff like that. Alright. You don't have to remember this, okay? I'll be honest with you, I looked it up. I don't make capacitors. I go like anybody else, I buy capacitors. But I thought it would be interesting for you to understand where that capacitance comes from. The basic formula for capacitance is 0.0088 Ka over D times the quantity N minus 1 times 10 to the minus 5th microfarads. Now what does that mean? Got a whole bunch of letters and numbers there. Well, A is just the area of one plate. So it's the size, the area of that plate. Because remember, a capacitor is just nothing but a couple plates or whatever put together with a insulator separating them somehow, and which can be air, can be vacuum, can be any number of things. Alright, so area of one plate is A. N is the number of plates, such as a tuning condenser. You can have a lot of plates. You can have lots and lots of plates. And D is the separation of plates. How close are they together? And K is just a constant. It's a dielectric constant. Every type of material and everything has its own. I listed just a few here. Air is 1.00. It actually is 1.00084, but 1 is fine enough. So air's got a dielectric constant of 1. Polyethylene is 2.25. Polypropylene is 2.2. Mica ranges from 3 to 6. Mylar is 3.1, and glass ranges from 5 to 10. The reason mica and glass has got a kind of a range is purity, different, and what types of other materials might be in it, and the like. So, and there's a whole bunch of others. You got wax, I think is like ranging somewhere from 2 to 4. Paper is like 2.08 or something of that nature and stuff. So, but anyway, I thought you just might find this kind of interesting. But that's where the capacitance comes from, and it's basically how big are the plates, their area, how close together are they, and how many are there, and then what kind of dielectric I got in between them. And that gives you capacitance. And that's basically all it is. And that's how it's figured. Now, as far as if you got a question about dielectric strength, air's got somewhere in the vicinity, I think it's 6 times 10 to the minus, or 10 to the 6 volts per meter. A lot of other stuff, it'll range on up to upwards to 7 times 10 to the 7th volts per meter. So that kind of gives you some general idea. Now meter is just how thick it is. 1 meter thick. So anyway, I'm going to probably drop off right here, and in the next video on this, as we move on, we'll talk about capacitors in series and parallel, and in capacitive reactance, and how a little more deeper into some of this stuff, and we'll move into some of that and on the next video. So thanks for watching, and thanks for your comments and stuff. I put up a video before this one. It was some stuff I got from an auction. You might find it interesting. So until the next video, thanks for watching, and I'll see you on the next one.